Good afternoon, students. So this is the first live session for the NPTEL course, Probability and Statistics, offered by me, that is Professor Somesh Kumar. We have actually 3 live sessions, and this is a 12-week course. So today I will review the contents which are covered in the first 4 weeks. So starting from the first week, we started with the algebra of sets. So of course you may think that this is a course on probability. So what is the need of algebra of sets, which is slightly different mathematical concept? So basically we define the probability function over a class of subsets which satisfy a certain characteristic, which we call basically a sigma field or a sigma algebra. So for that purpose, we need some algebra of sets. So we define what is a class. So a class of sets is actually a set of sets. So we have a universal set, and then if we consider subsets of that set, and we consider some certain number of sets which are contained in particular set, that is called a class. At the same time, then if we consider few classes and then we consider a set of classes, that is called a collection. Certain basic characteristics are, for example, we define what is an indicator function of a set, and then we define a sequence of sets. So when we consider basically various sets, like we consider the sequence of numbers, we can also consider the sequence of sets. And once the concept of sequence comes, we define what is a limit inferior, limit superior, and the concept of the limit of the sequence of sets. So basically, limit of a sequence of set is also another set, but it is obtained in a particular way. For example, limit infimum is the set which is basically the set of all those points which are contained in all but finitely many number of the sets of that sequence. Similarly, the limit superior is the class of is the set of those points which are contained in all but in infinitely many sets of that sequence. Naturally, the limit inferior set is always subset of the limit superior, and when the two are equal, it is defined as the limit of the sequence of the sets. After that, we talk about various terms. So what we call as the ring. So this is an algebraic structure. So ring is a class of sets which satisfies two properties. That is, it is closed under the differences and the union. So here we consider only finite. So if I have A and B two sets, then A union B will belong to the ring, A minus B will belong to the ring, if it is closed under that. When we consider infinite operation in the sense of union, then it becomes a sigma ring. Similarly, another structure is field or an algebra. So it is again closed under two operations. One is the operation of complementation. That means if A belongs to a field, then its complement also belongs to the field. And if there are two sets, A and B, then A union B also belongs to that. So now we can extend it to include the countable unions. So that will become a sigma field or a sigma algebra. Okay, and of course, then similarly we define a monotone class. That means class of sets which is closed under the operation of limits. It is called a monotone class. There are interrelations. For example, a sigma ring is always a ring. A field is always a ring. A sigma field is a ring. It's a sigma ring. It's a field. And then we move to the concept of what is a random experiment. So we have defined in detail and we have given several examples. Because in probability, we deal with experiments which have outcomes which are not necessarily deterministic in nature. So for example, what is the weather? How much is the temperature? What would be the total agricultural production of a particular crop? What would be the growth rate of the economy? what would be the number of people, say, suffering from a certain disease, and so on. So when we try to analyze probabilistically, that means what are the possibilities, then that is random experiment. Then next we define the concept of event. So event is a set. So a sample space is a collection of all the outcomes. So it is a, you can say, a set, or you can say a universal set in a particular random experiment. And then we consider the classes of subsets of the sample space. These subsets of the sample space, they are termed as events. So that is the reason that why we have to give the algebra of sets here, because now the events are nothing but the sets here, and the class of the events we consider in such a way that it is actually a sigma field or a sigma algebra. Then a probability function is defined as a function which takes value between 0 and 1. It is having the domain as any of these event sets, and it satisfies three axioms which are called Kolmogorov's axioms. Namely, it is greater than or equal to 0. The probability of an event is greater than or equal to 0. The probability of the total sample space is equal to 1. And the probability of a countable union of sets of disjoint sets is equal to the sum of the probabilities. This is called Kolmogorov's axioms. So we have an axiomatic definition of probability. Now, this is basically providing a mathematical framework under which all the probabilities lie. That means they should satisfy, any valid probability function must satisfy that. And you have actually initially the classical and the relative frequency methods, which were given by basically Laplace and the von Mises, that we have discussed in detail. So basically they are nothing but the methods for calculation of the probabilities in various problems actually, and ultimately they must satisfy the axiomatic definition. That means they must fall into this framework. So we consider then the probabilities of the properties of the probability function. So for example, probability of A complement is equal to 1 minus probability A. We have for example, if I have a finite number of disjoint sets, then the probability of the union is equal to sum of the probabilities. If B is a subset of A, then probability of A minus B is equal to probability of A minus probability of B, and so on. Following up from here, we have the additivity property, that is called addition rule. That means if I have probability of A union B, then it is equal to probability of A plus probability of B minus probability of A intersection B. There are extensions of this. So we have a general addition rule. If I have 3 events, or if I have n number of events, then what is the probability of the union of those events? From here, we also have something called Bonferroni's and Boole's inequalities, which satisfy, like if you have probability of a union, then it is less than or equal to something, it is greater than or equal to something. Following this, we define the concept of conditional probability. So if I have events A and B, what is the probability that an event A occurs, given that we have the prior knowledge that the event B has already occurred? So this is called the concept of conditional probability. So that is of great importance in the theory of probability. And then we follow up by multiplication rule, the general multiplication rule. In particular, it leads to analyzing events based on various possibilities. So that gives you the theorem of total probability. That means if I have an event A, so it is can be considered as an effect, and that effect is caused by several causes. So for example, if I am analyzing, say, accidents on a road, so whether the accident is caused by driver's negligence, or it is caused by certain defect in the design of the road, or is it caused by some mistake of opposing vehicle which is coming from the other side, or it can be any other reason. So if we try to analyze an event in terms of various things, then we get the theorem of total probability. A follow-up of this is, which is called Bayes theorem, which gives the reverse. That means what is the posteriori probability of an event given that an outcome is already available to us. These results are of fundamental importance in the theory of probability and also development of subsequent distribution theory. We also give the concept of the independence of the events, and the concept of the independence of the events is that if events AIs are independent, then the probability of intersection or probability of the simultaneous occurrence of AIs is equal to the product of the probabilities of those events. Following this, we have solved a large number of problems which are related to various kind of experiments, and one can look into that. So students are in particular encouraged to solve all such problems so that they get understanding of how the theory of probability can be used for solving various kind of problems. Next, we consider the concept of random variable. When we consider the probability of an event, then we are considering event and what is its probability. But in many practical applications, the events are too descriptive. For a mathematical treatment of such random experiments, one can consider numerical values against each outcome or each point of the sample space. That is nothing but the random variable. So the probability function which we define for the event can be transferred to, or you can say induced on the values of the random variable. That gives rise to the probability distribution of a random variable. Now, in particular, we have two special kind of random variables. One is that when the random variable takes a finite or countably infinite number of values, then it is said to be a discrete random variable. In this case, the probability distribution is described by a probability mass function, and this probability mass function is nothing but the assignment of the probabilities of the individual values of the random variable. So suppose theoretically speaking, if I say the random variable x takes values x1, x2, x3 and so on, then the probability that random variable capital X will take value small xi, that is denoted by pxi, that is the probability mass function. So because of the probability function, it is satisfying the two properties. That means the values lie between 0 and 1, and sum of all the values is equal to 1. On the other hand, we can have random variables, for example, a time or a weight or some other quantity which are taking values on an interval. If the values of the random variable are defined on an interval, then in place of the probability mass function, we have a probability density function. So this probability density function, again, it is satisfying two properties, that the function is non-negative and the integral of the function over the entire range of the values of the random variable is equal to 1. These are the two broad classifications of the random variables, that is the discrete and continuous random variables. However, there can be situations in which a random variable can be a mixed random variable. That means there can be some set where it will take finite number of values, and then there is another set where it will take values on an interval. Such random variables are called mixed random variables. So one can have a broader representation of a probability distribution of such random variables, which is by a cumulative distribution function. So in the case of continuous random variable, the derivative of the cumulative distribution function is the probability density function almost everywhere. And you can say that the probability distribution function or the cumulative distribution function is nothing but the indefinite integral of the probability density function. In the case of discrete random variable, it is the cumulative sum up to that particular point. And if you want to find out the probability mass function at a point, then you take the difference between the two consecutive points, the value of the probability distribution function. Next, we consider the characteristics of the random variables. which are defined, like we consider the concept of moments. So we have the concept of the mathematical expectation. So we have the mean value of a random variable, the variance of a random variable, or the which describes the dispersion. The mean value means that it defines the measure of central tendency of a random variable. And then we can have the higher order moments, which are used to describe the shape of the distribution in terms of like the symmetry or non-symmetry of the distribution, the peakedness or the flatness of the distribution. So these are called the measures of skewness and kurtosis. In particular, the first four moments of are more importance. We also have the points on the CDF, or you can say on the plot of the PMF or the PDF, which is called the quantile. So you have the median, that means it divides the distribution into two parts. That means the probability up to that point is half, and beyond that is also half. You have the concept of quartiles, which divides the distribution into four parts. You have the concept of deciles, percentiles, and so on. We have then the concept of moment generating function. Moment generating function, apart from giving moments, is even more characterizing function of the distribution, because it is uniquely related to the probability distribution. So in many cases where we determine the probability distribution, but it is difficult to analyze or obtain it, and if we are able to find out the moment generating function, then it is easy to identify the moment generating function. In the next topic, we have considered certain probability inequalities. Now, these probability inequalities relate the probability of a random variable taking values in a particular set, and it is bounded either above or below by a quantity which is calculated based on the moments of the distribution. In particular, in the Chebyshev inequality, if I say x is a random variable with mean mu and variance sigma square, then it gives that the probability of modulus of x minus mu greater than epsilon is less than or equal to sigma square by epsilon square. And this is true for all epsilon positive. So there are many cases where we have only limited information on the random variable, but we can say something about the range of the probability where the values of the random variable will lie. Extensions of this Chebyshev inequality are Markov inequality, and then even further generalizations. Thereafter, in third week, we have considered specific discrete distributions. So we have considered distributions which arise in trials, which are considered, we call them as the success failure trials. So the success failure trials are like, for every outcome we define only two possibilities. That means one type of possibility is called a success, another type of possibility is called a failure. This gives rise to Bernoulli distribution, and an extension of that. That means when we consider n number of trials which are conducted independently under identical conditions, then the distribution of the number of success is called a binomial distribution. Uh, Now, further usage of this Bernouillian trials is in the description, where we consider the number of trials needed for the first success, which gives a geometric distribution. The number of trials needed for first time rth success is observed, that gives rise to the negative binomial distribution, and so on. We also consider finite population distributions. So a finite population of size n is divided into two parts. Say, for example, people who are having education up to class 12 and those who are having beyond. So if we consider one type of population size as m and another size as n minus m, and if we take a random sample of people, say of size is small n, then how many of them belong to the first group, how many of them belong to the second group? This description of the probability distribution is called a hypergeometric distribution. Once again, there are interrelationships between these random variables. For example, as the population size converges to infinity and such that the proportion of one type of items remains converges to a certain number p, then this distribution converges to a binomial distribution. Now, even this distribution, binomial distribution, as n becomes large and p becomes very small, such that np converges to something called lambda, it converges to a Poisson distribution. So, which is another discrete distribution. Then we have this Poisson distribution actually arises in a process. So we consider something called events occurring over a time, events occurring over an area, events occurring over in a space. They are said to follow a Poisson process if they satisfy certain assumptions. What are these assumptions? Suppose we consider time, events occurring over time. So if we consider the events occurring over time, uh, and if we consider disjoint time intervals, then the number of occurrences are independent. That is one of the assumptions. Second assumption is that the probability of a single occurrence in a small time interval is proportional to the length of the time interval. Third one is that the probability of more than one occurrence in a small time interval is negligible. Then under this assumption, the distribution of the number of occurrences over a time interval, it is following a Poisson distribution. So we have derived the distribution of the number of occurrences in a Poisson process as a Poisson distribution. And also there is another way of obtaining the Poisson distribution. It is through the limiting approach to the binomial distribution. So for example, if we are considering say number of traffic accidents, the number of say number of natural calamities and so on. So these are all examples of the events occurring over a Poisson process. Thereafter, we have moved to the concept of continuous distributions. So if the events are occurring over a Poisson process and we start from a given time and we note down the time at which the first occurrence is observed, then the distribution of this time is following an exponential distribution. This exponential distribution has some interesting properties. For example, it has a memoryless property. So for example, if I say x is following a exponential distribution with parameter lambda, then probability of x greater than say s plus t, given that x is greater than s, it is same as the probability of x greater than t. So that means the starting point does not make any difference. This is called the memoryless property of the exponential distribution. Then we consider the shifted exponential distribution. A further extension of exponential distribution is that when we observe rth event for the rth occurrence in a Poisson process, then that is following a gamma distribution. We define, so when we consider positive valued random variables, many times they are referred to as the lifetime distributions. So for example, if we are considering the life of an equipment, the life of a organism and so on, that means the time to take for completion of certain process. So these are all examples of the lifetime distributions. And so there we have the concept of the reliability of a component, the failure rate of a component. So reliability of a component is nothing but the survival probability at a particular point time t. Okay, and we define based on that a failure rate. For the exponential distribution, this failure rate is constant. And so that means it's a robust system actually. Whereas in general, the failure rate will be decreasing. You can of course have different kind of examples where you have a bathtub shape of a failure rate. You can have a cap shaped or a hat shaped failure rate function and so on. So these are some of the important distributions in the lifetime studies. In particular, it gives rise to Weibull distribution, etc. We discussed some other distributions also, for example, a beta distribution, double exponential or Laplace distribution, and also the distributions of the order statistics. So, what are order statistics? Many times we are not interested in the raw data, rather than we are interested in the ordered data. For example, if there is a competitive examination, then we are interested in the marks of the student who scored the maximum, marks of the students in an order, like who is the second, who is the third one, and so on. Same thing happens in many other practical situations. For example, there is an interview board, so we look at candidates which are in the higher ranks. So when we look at this data, that is called order statistics, and one is interested to find out the distribution of the maximum of the observations, the distribution of the minimum of the observations, and so on. So we have discussed in detail the distributions of the order statistics. So in a nutshell, actually, till the first 4 weeks, this is the thing that we have completed. If you have any questions, then you can pose those questions. Is there any question on the YouTube?
They are asking about PPT. What the question is there?
Yeah, PPT is not there. See, I am teaching, actually I am writing in full detail, so you can take the shots of those, screenshots of those things. So that is basically the lectures here available. Yeah. Any other questions?
No other questions.
Okay, so if there is no other question, then I will like to stop here. Okay. Hello.
Hello, sir.
Then I will stop here now.
Okay.
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 Yeah. Okay.